So in this video, I'm going to be showing that the fanning friction factor is always 16 over the Reynolds number for laminar flow. And kind of how I'm going to do that is we're going to start with a controlled volume cylinder inside of a pipe. I'm going to derive the force balance on that. Then we're going to be able to use the force balance to get the velocity profile equation. From the velocity profile equation, we can get the volumetric flow rate, and then from that we'll be able to apply Bernoulli's equation and show that the fanning friction factor is 16 over Reynolds number. So here I've drawn a picture of our controlled volume cylinder. It's this cylinder inside of our larger pipe. I've defined the pipe to have a length of delta x, and I've also drawn two pressure forces on the drawing. So to start with, like I said, we're going to go ahead and derive the force balance. So the first force that we want to look at is the pressure force on the end caps. And so there's going to be one due to on this side, and then there's going to be pressure force on this side. And to express that mathematically, we're going to have P1 minus P2. So that's the net pressure on the end caps times the area, which is just going to be pi r squared. And so in addition to the pressure on the end caps, there's also a shear force from the liquid moving by our controlled volume cylinder. And we can express that using the shear rate, tau, times the area. So the area is just going to be 2 pi r times the length of our pipe. So the circumference times the length. And so then from here, if we assume that we're working with a Newtonian fluid, tau is going to be equal to mu times dv over dr. And we can go ahead and plug this into our equation and start to get at the velocity profile equation. So I'm going to go ahead and move this term to the other side. And so on the left, we're going to have mu times dv over dr times 2 pi r delta x equals negative p1 minus p2 times pi r squared. And so then I'm going to go ahead and solve for dv over dr. So we're left with p1 minus p2. We're going to divide over by pi, so these will cancel out. Divide over a 2. Divide r, so this just becomes r. We're going to divide delta x, and then divide mu. So this is our equation after doing that. And then we can go ahead and just take the integral of this equation. So I'm not going to separate the variables and put bounds in because that'll complicate things a little more. We're going to go ahead and integrate this, and then we'll have a coefficient of integration that we can solve for, and then we'll have our velocity profile equation. So I'm just going to give myself a little bit of room and start back up here. So once we take the integration of this, we're going to have all of our constants still out front. And then the integration of r is just going to be r squared over 2. And like I said, we're going to have the constant of integration. Now we can go ahead and use a point that we know to find this constant of integration. And the point that we're going to use is where r equals big R. Because at this point, the velocity is going to be equal 0 because it's against the side of the pipe. And then we can go ahead and just plug this in and solve for C. So we're going to have the two pressures over 2 times the length of the pipe times the viscosity times big R squared over 2 plus C. So now we can just move this whole term to the other side of our equation. and that is our value for C. So I'm going to write it over here. Actually, I'm just going to write the whole velocity profile equation out down here. It's going to be P1 minus P2. I'm actually going to get rid of this negative sign and factor out all of the constants. And so since we have r squared over 2, there's going to be a 4 down here times delta x times mu times big R squared minus little r squared. All right, and now from here, we can go from our velocity profile equation to the flow rate using the idea that the volumetric flow rate is the average velocity times the area. And so we're going to need to take the integral of this equation. We're going to kind of think about adding up a bunch of different rings on the surface that have the width of dr to get our average velocity. And so to get q, we are going to have the integration from 0 to r p1 minus p2 over 4 delta x times mu times r squared minus r squared, big R squared minus little r squared, times the area of our differential pieces that we're adding up. Which are just going to be 2 pi r dr. So now from here, I can erase all of this and go ahead and integrate this and plug in our bounds of integration. So Q is, I'm going to move all the constants back out front. We also have a pi, and then we're multiplied by 2, so this is just a 2 in the denominator. And then we have the integration. I'm going to distribute this r right here. And so we have the integral from 0 to r of big R squared times little r minus little r cubed dr. And now again, I can take the integration, leave all of the constants out front, and the integration of big R squared times r is just going to be big R squared times little r squared over 2 minus little r to the 4th over 4th, and then this is evaluated from 0 to r. And so once we plug in our bounds of integration, anything with that we plug in 0, so both of these terms are going to go in 0, and then when we plug in r, we're going to have big R, I'll write it over here. We'll have big R to the 4th over 2 minus big R to the 4th over 4, which is going to leave us with big R to the 4th over 4. So for our volumetric flow rate, we have pi times P1 minus P2 over 2 times the 8, or 2 times the 4, which is 8 in the denominator, times delta x times mu times r to the 4th. And so now we have our volumetric flow equation. So from here, what we need to do is we need to get it in terms of the diameter, and then we could apply Bernoulli's equation and go ahead and show that the fanning friction factor is always 16 over the Reynolds number. So to put this in terms of the diameter, we just have to keep in mind that r equals d over 2. So our new equation for q in terms of diameter, really not much changes. We still have pi times the first pressure minus our second pressure over 8 delta x times mu, but instead of r to the 4th, we now have d to the 4th over 2 to the 4th, which is 16. And so this gives us pi times P1 minus P2 d to the 4th over 128 times delta x times mu. So now, like I said, from here, we can go ahead and apply Bernoulli's equation to this problem. And since the R diameter is not changing, we don't have to worry about change in velocity. And since our pipe is flat on the ground, we have no change due to potential energy. So for this problem, the Bernoulli's equation is just going to be the pressure at location 2 minus the pressure at location 1 over the density times the negative friction factor, frictional heating coefficient. So now we can go ahead and plug in. We can rearrange our equation for the volumetric flow for P1 minus P2, and then we'll be able to plug it into our Bernoulli's equation. So just kind of solving for these. We're going to multiply by 128. We have Q over here multiplied by delta X and mu. And then divide by pi and d to the fourth. So once we solve this equation for P1 minus P2, we can go ahead and actually plug it in here because we can multiply both sides by -1. That way this term is positive on the right, and that'll flip this to P1 minus P2, so we can plug it in. So we're going to have 128 times Q times the length of the pipe times the viscosity of the fluid over our density of the fluid times pi times d to the fourth. And this is going to be equal to our frictional heating coefficient. And so from here, to kind of put this in terms of our fanning friction factor, oftentimes in engineering, the coefficient, the frictional heating coefficient is expressed as this. So I'm going to go ahead and plug that in for F. And so we have 4 times the fanning friction factor times delta X over the diameter times the velocity squared over 2. Now from here, we just need to kind of massage this equation and solve for F. So the first step I'm going to do is kind of erase this over here. And then we need to rewrite Q, the volumetric flow, in terms of the volume times the area. So Q is just going to be equal to the volume times pi d squared over 4, which is just the area in terms of the diameter. So going to go ahead and plug that in. So we're going to have 128 divided by 4 is 32. Yep, 32. Times V. Pi and pi cancel out. So we have V times d squared cancels out with this d to the fourth. So we're just left with rho d squared in the denominator times V times delta X times mu. Let me just double check that's right. That looks right to me. So I'm going to go ahead and continue. Just rewrite the right side of the equation. And now I'm going to start solving for F. So to solve for F, we need to divide by 4 and then multiply by 2. So we're dividing by 2, and that just gives us 16. Next, we have V. We need to divide by V squared. So in the denominator, we're just going to have V to the first power. The delta X's are going to cancel out. Then we're going to multiply by D, so this is going to cancel with this to just be D, and we'll have rho that carries over times viscosity And now I have Reynolds number written over here, and that is rho dV over mu. Well, here we have the inverse of Reynolds number, which is mu over rho dV. So we can rewrite this as 16 over the Reynolds number. So fanning friction factor for laminar flow in all cases is 16